Now you might wonder, how do we identify the line that we have to use to map the independent variable with the dependent variable, or what should be the equation of the line, what should be my beta naught hat value and beta 1 hat value. So how do we find these values? So in this video we will talk about how do we arrive at the values of betas. So betas in the sense beta 1 and beta naught hat. So how do we find their values? So the answer to that is we try to minimize the errors. We try to find the equation of the line which minimizes the sum of squared error. So in this graph you can see we have around 10 points in this graph. So the line has been made using the 10 points, and the line does make some errors. So the errors are represented as E1, E2 till E10. So the errors made by this line in this graph are represented by E1, E2, E3 all the way till E10. Now how do we identify which line to select? So what we do is we try to minimize the sum of squared errors. So we square each of the errors, we add them up, and the entire quantity that we get, we try to minimize this. So while we minimize this quantity, we arrive at the values of beta naught hat and beta 1 hat. Now let us see how do we do this. So to find out how we get the values of beta naught and beta 1, if we minimize this, we'll have to go deeper into the maths of linear regression. So let us go into the maths of, and specifically it includes calculus. So how do we minimize a quantity? How do we minimize any mathematical function? In order to minimize any mathematical function, we take the derivative of it, we take the first derivative of it and make it equal to 0. And then if we solve the mathematical function, we get the point at which the mathematical function is minimum. So let us do the same here. So from high school we have learned that if we have to minimize a function g of x, what we do is we take the first derivative of the function and we make it equal to 0, and then we solve for x, and whatever x we get, that is the point where this function is minimum. So that's what we'll be doing here. So in this case, as we saw here, we try to minimize the sum of squared error, which is also represented as SSE, sum of squared error. So let me write it in another way. So since it is sum of squared errors, I can write this as actual minus predicted. So y hat represents my predicted values, and I will square this quantity and take the summation of this from 1 till 10. So in this case I have 10 points. So I'll take the summation of it from 1 to 10. So this quantity basically represents my errors. I can also write this down in another simplified form. Minimize EI whole square, where I goes from 1 to 10. So then I will get this equation. So that is what I have written here in slightly different form, in the form of actual minus the predicted. Now let us evaluate this. Let us break this down into smaller pieces. So I will write minimize. Once again I will write actual minus. Now instead of writing predicted here y hat, let me use this equation. Now we know that predicted value is equal to beta naught hat plus beta 1 hat x. So I will write that down here. So beta naught hat minus beta 1 hat x, and square of this entire quantity. So we are trying to minimize square of this entire quantity summed over 1 to 10. So this is what we'll be doing. Now we have two unknowns here. We have two unknowns in this equation. One is beta naught hat, and one is beta 1 hat. Now let us try to minimize. As we saw from calculus, to minimize this we will have to differentiate it. So differentiate with respect to what? We will differentiate this with respect to the unknowns in this equation. So what is unknown? The unknowns is beta naught and beta 1 hat. So remember here we differentiated it with respect to x, because x was the unknown. X was what the function depended. In this case, our function depends on the value of beta naught and beta 1. So we will differentiate with respect to both of them. Now since we have two variables involved here, we will have to do a partial differentiation. So this entire function, this entire equation, I will differentiate it with respect to beta naught first, and once again with respect to beta 1 hat. So I will make a differentiation here and I will get two different equations. So one equation here, one equation here, and I have two unknown quantities. If I solve those two equations, I will get the value of beta naught hat and I will get the value of beta 1 hat. So this is how we calculate the value of beta naught hat and beta 1 hat using high school calculus. Now we don't have to do this actually when we run a linear regression example, because the software that we'll be using, be it R or Python, will do this for us. So we will directly be getting the values of beta naught and beta 1, but this is very important to understand how actually the software is calculating beta naught and beta 1 values. So to recollect what we have covered in this video, we covered that how do we arrive at the equation of the line. So we arrive at the equation of the line by minimizing the sum of squared error. So we minimize the sum of squared error and hence we get the values of beta naught hat and beta 1 hat. And of course if we have the values of beta naught hat and beta 1 hat, we have our predicted values. So we can make predictions using the x variable. Now this entire process that we just discussed is known as OLS. So this is an algorithm that is used which is known as ordinary least squares. So ordinary least squares, because we are calculating the squares, so it is known as ordinary least square. So linear regression follows the algorithm ordinary least square, which tries to minimize the sum of squared errors, and in that process it calculates the values of beta naught hat and beta 1 hat, which helps it to arrive at the equation of the line which is used to make predictions.